The subject is laser-produced plasmas and LPP soft X-ray and EUV sources for laboratory astrochemistry. I would like to say that I'm not astrochemist. I am not astrophysicist, but I'm working with plasma, laser-produced plasmas or discharge plasmas. But in our laboratory, we have possibilities to perform so-called experiments of so-called laboratory astrochemistry. I will tell some words concerning what is it, laboratory astrochemistry, and what kind of experiments are being performed in different laboratories. And then I will present our installations, our sources, and I will show some experiments that were performed in our group that indicate some possibilities of using it for experiments concerning this laboratory astrochemistry, concerning interstellar dust, interstellar ices, Titan's upper atmosphere, formation of tholins, and some experiments concerning comet atmosphere, formation of comet atmospheres. So at first, what is interstellar dust? We have to realize that interstellar dust is something very different from the dust in our room or in the Earth's atmosphere. This dust is mainly formed from carbon. You can see, for example, an infrared spectrum of a variety of carbon-containing molecules with a variety of carbon atoms. In such nebulas, for example, we can have a very complicated, very complex carbon compounds, but in principle, there are so-called polycyclic aromatic molecules, hydrocarbons, and they contain very large amount of carbon and hydrogen atoms. But there can be also linear molecules originating from polymerization of acetylene. So, and these long chain or these polycyclic molecules form the interstellar dust. And what can be done in a laboratory? In laboratory, such similar molecules can be formed using, for example, plasma systems. Of course, low temperature plasma systems, because in high temperature plasma there are no molecules. So this is an example of such plasma chamber equipped with, let's say, a variety of instruments that allow for measurements for detection of such large carbon molecules. You can see, for example, two spectra, molecular spectra, mass spectra that were obtained in experiments where electrical power was applied to form the plasma in in a mixture of acetylene and helium or argon. And depending on the composition, we have different spectra. Nevertheless, we have a large number of carbon in the molecule. In this case, it is 12. There are even more. In the other experiment, laser scattering was employed for in similar experiment. I mean, there was also a discharge in carbon-containing molecule gases, and in this case, carbon dust was formed. You can see here an image of scattered light, laser light, and cross sections corresponding to average dust particle density, and with time development of their sizes. There are also special machines like Stardust machine that are prepared for creation of sputtering, let's say, of carbon material to atoms, and these atoms are introduced to a chamber where they are joining each other, forming more complex molecules with addition of hydrogen. And in this chamber, we have this type of densities. There's next chamber where some beam of these carbon particles are injected, and there are possibility to perform some measurements. The material is deposited, for example, on this plate, and in this next chamber in this plate. And there are also mass spectrometers that allow for detection of measurements of masses of the dust particles. The plate where the carbon molecules, carbon-containing molecules are deposited, is being cooled, and then it can be heated, which allows to simulate some conditions around so-called AGB stars, where streams of carbon are ejected into surroundings. Such processes are being simulated numerically, of course, also. And here you can see some time development of appearing of the various molecules. And there's a chain of reactions leading to formation of complex carbon-containing molecules. The interstellar dust is can be even very can be even more complex, because the dust is very cold. Its temperature is at the level of a few kelvins, and on such dust, gases like CO2 or CO, nitrogen, etc., can be deposited from forming the interstellar ices. And there are some experiments, especially also some specially prepared chamber installations, allowing for investigations of such interstellar ice analogs. This is one of the examples. And here you can see cryogenically cooled plate. On this plate is deposited material originating from different gases present in in the interstellar medium, like, for example, CO2, CH4, etc. And they are deposited on this plate. Then they are irradiated by UV light, and it is warmed up, and there is also interaction of high energy photons with the ices. So as the consequence, the ice is changing, emitting some volatile molecules. And they can be detected using mass spectrometry or infrared spectrometry. Also, the excited molecules can be detected by using UV spectrometry. What is it for? Please look at this spectrum. It is part of the infrared spectrum. When we observe what is using sky telescopes, we observe the spectrum from space, we can see something like that. This is a spectrum originating from the dust and the interstellar dust. This is the spectrum from pure CO2 ice. So it is very, very different. And we can, by performing the laboratory simulation of this interstellar dust, we can fit this spectrum to the observed spectrum. This way we can know or conclude what is what we can see using the telescopes. There are also experiments using synchrotron radiation, high energetic photons, not only UV but also EUV, from in this experiment from 50 to 150 nanometers. And this radiation is irradiating the special photocell. In this photocell is filled with some gas mixture. It can correspond, for example, to upper Titan's atmosphere. So the mixture contains nitrogen and methane. And the gas is flowing through this cell and is irradiated by the synchrotron radiation. In such case, the products are detected using mass spectrometer, and here you can see the spectra. And again, we can see that complex carbon organic molecules are being formed. There are also other experiments also concerning processes in atmospheres, but atmospheres of exoplanets with a primitive atmosphere. And in this experiment, there was a mixture of gases in a special container. There was focused laser radiation. The laser, it was pulse laser from Prague, and it was irradiated by multiple shots, and some molecules were formed inside. This container was then connected to infrared spectrometer, and the spectrum was obtained, which is visible in the bottom of this slide, and is compared with some observations. So we can identify a number of complex molecules, organic molecules that were detected in after irradiation using this laser pulse. Of course, it is not direct interaction. The interaction was connected with plasma, laser-produced plasma. This plasma was exposed to the surrounding gas, and the low-temperature plasma this way was formed, and in this plasma were these processes leading to those molecules. The next type of experiments concerns so-called tholins. Tholins are disordered polymer-like materials that were found in Titan by Huygens Lander, and probably they form also this reddish places in Jupiter's satellite Europe. And the Huygens Lander detected, made such photograph, and the Cassini mission detected such complex molecules with a large number of mass, with large masses, which means that there were large numbers of carbon atoms in each molecule. And these were so-called tholins. And such tholins can be produced in a laboratory, also in plasma systems. For example, in a cosmic, which was built in NASA, and there's a discharge between two electrodes, and the gas mixture is injected through this electrode system, and forming the low temperature plasma, where tholins are being formed and deposited on these plates. Then they were investigated using, the plates with deposited material were investigated using Xenes method. And here you can see the spectra indicating formation of tholins. Such tholins can be also produced in this type of plasma generators, where with RF power supply, and they're also deposited in this case on a variety of plates, substrates, cooled, however, not cooled to cryogenic temperatures. It is not necessary. And these plates can be then removed and investigated. The material can be investigated using, for example, infrared spectroscopy. And here you can see the spectra that were obtained for such formed tholins. There are also comets, cometary material, especially cometary atmospheres. And there was a mission, Rosetta, with the land where a probe was landed on the comet, and not everything worked properly, but a large amount of organic molecules were detected. And what is important for laboratory astrochemistry, it is the question, what is the origin of the material in comet atmosphere? There is hypothesis that in the cometary nucleus, we have complex molecules, polymer molecules, and these molecules are irradiated by the sun photons, and these photons destroyed the bonds, and some volatile molecules are being emitted and detected in the atmosphere. So this type of experiment was also performed using such molecules irradiated by EUV light, and the products that were obtained were similar to those detected in cometary materials. Okay, and now let's go to our laboratory. We have several systems with laser-produced plasmas, which are in principle sources of EUV or soft X-ray radiation. This is one of such systems. It is composed of three sections. In one section, we have laser-produced plasma. In the second section, we have the optics, EUV optics. And in the last section, it is the irradiation. It is the irradiation chamber, and there can be variety of experiments possible to be performed. For example, irradiation of materials, irradiation of gases, etc., etc. But it is in some sense similar to this system, which was used for laboratory astrochemistry experiment using synchrotron. This photocell, in our case, this section of the chamber. This is the source corresponding to this synchrotron beam. And here we have the system with mass spectrometer, like here. So in principle, we can perform here similar experiments. This is the spectrum of the radiation. So the maximum, as you can see, is at approximately 11 nanometers. So it is even much more, the photons energies are higher than using this synchrotron system. Of course, the radiation can be also selected using proper filters. And this is our second system with larger laser, and in this case we can obtain even soft X-ray photons. Depending on gases that are used for plasma creation, we can obtain a variety of spectra. This is, for example, for xenon, it is for argon. And here you can see the pulse duration. It is in a region with long pulse, long laser pulse, and it is with short 1 nanosecond laser pulse. Here you can see images of plasmas. This is in visible range, this is in EUV range, and this is in scattered laser light. And you can see a time duration of emission in various ranges of photon energies. It is in EUV range, it is in UV range and visible range. So the in visible range we have microsecond scale, in EUV we have nanosecond scale. We have also developed a special target, a so-called aerosol target, where it is possible to add some chemical compounds, giving other spectra than only from pure gases. The radiation emitted from plasma is emitted in full angle, 4 pi. So part of the radiation can be collected using a special mirror, for example, ellipsoidal mirror, like in this case. And in the focus of this mirror, fluence of the radiation is at the level up to half joule per square centimeter. This is the spectrum of the reflected light. Here you can see the image in visible range and the focal spot, the size of the focal spot. This is the trace obtained on some glass surface after interaction with of the focus beam with glass. For focusing, we can use not only the EUV collector, but also soft X-ray collector. In this case, these are two paraboloids. In one of the focus, we have plasma, and in the second one, we have the focal spot, and we can irradiate various materials using the soft X-ray light, and the maximum of the fluence. In this case, it is approximately 250 millijoule per square centimeter. We can select also part of the spectra using multilayer mirrors. In this case, for xenon plasma, we can have maximum at approximately 13.5, 15.5, or 22. Of course, there can be also other mirrors. And using additionally special window with LIF window, we can select only the VUV radiation. From it is similar to when we take, for example, a special filter for Lyman alpha. We can select some part of the spectrum corresponding more or less to the Lyman alpha, which means the most common radiation in the space. We have also a special system with chamber that can be filled with gas under gas mixture under low pressure, and inside this chamber we have again a gaseous target to have dense plasma with for laser gas interaction, and there is LPP creation. This plasma, high temperature plasma, irradiates the surrounding gas, the ambient gas, and can form the low temperature plasma. So it is similar in some sense to discharge plasma systems. The gas which is injected through the nozzle to form the target has the same composition as the gas filling the chambers, so its composition doesn't change. And here you can see spectra in case of from laser produced plasma. In this case, it is spectrum from the mixture containing nitrogen, methane, and CO2. In this case, we have O lines, N lines, and C lines. And now I will present some experiments that were performed indicating that we can obtain similar molecules that are obtained in laboratory astrochemistry experiments. I will show. I'm showing again this system, which is similar to the system operating with synchrotron. This system was used for interaction of the EUV beam with polymers, and the polymers were fragmented into parts, volatile parts, and these parts formed the low temperature plasma. In this plasma, some reaction took place, And for example, in this case, we obtained such polymerized acetylene, which is not part of this polymer chain. It means that the reaction were in this low temperature plasma, forming something similar to this dust, interstellar dust. And using variety of polymers, we obtained in almost in every case such emission of such molecules. It means that we can perform similar experiments as they were performed using the synchrotron with or some UV lamps or VUV lamps, where there was interaction with some material, like, for example, this cometary, which is probably contained in cometary nucleus, which was fragmented into volatile parts and forming various carbon-containing molecules. By interaction of the focused EUV light with gases, it was possible to perform experiments with gaseous mixtures, and we employing the UV, the spectrometer for UV and visible light, we obtained such spectrum corresponding to formation of CN molecules, radicals in principle, which was detected also in other laboratory astrochemistry experiments. In similar system, but without the UV optical system, also low temperature plasma was formed, and in this plasma C2 molecules were detected. You can see here the molecular spectrum in the visible light. Unfortunately, in using this spectrometer, it was not possible to detect more complex molecules. So it requires employing, for example, a mass spectrometer, like in this case. So we are going to do that. Also, in this chamber with ambient gas, we performed similar experiments, and also we obtained the molecule CN. We detected the CN molecules in gaseous mixtures containing nitrogen and CO2 or methane. In principle, we can also, after multiple shots in such system with ambient gas, we can take a small sample of this gas to a special cell, which is dedicated for measurements in infrared spectrometer. And in this case, we can detect molecules which were formed and remain in the gaseous mixture after multiple shots. And here you can see that we detected the HCN molecules formed in a mixture of CO2, methane, and nitrogen. There was also experiment where we irradiated the CH4 and nitrogen mixture, and we also measured what was formed in the chamber, and you can see here some part of the spectra corresponding to formation of acetylene, which was not present in the initial gas mixture. It means that it was formed there. And acetylene, unfortunately, it was not possible to detect more complex molecules, but at the walls of the system, after multiple shots, there was deposited amorphous carbon, which means that some carbon dust was also formed there. So we could also experiments corresponding to the formation of dust in space. I showed in one of the previous slides an experiment performed in NASA with cosmic system, where tholins were detected using the SANES method. We have also an instrument based on a laboratory plasma source, allowing for such measurements, and we performed experiments with a mixture of CO2 and methane and nitrogen, etc. And we obtained also such spectra, but these spectra were detected, obtained for the material deposited on plates. These spectra were obtained during operation of the system. So in principle, we could also perform measurements of the deposited material, and in this case, it should be similar to these results.
Andrzej,
so,
yeah.
I would like to summarize, and I would like to say that usually laboratory astrochemistry experiments are being performed using plasma or synchrotron-based systems, but laser-produced plasmas, especially EUV or soft sources, based on gas path targets, can be used for laboratory astrochemistry experiments instead of synchrotron of UV lamp or UV lamps. And laser plasmas produced in gas path targets operating with the ambient gas can be used also for laboratory astrochemistry experiments as an alternative to discharge plasmas. And finally, I would like to say that some initial experiments concerning laboratory astrophysics, astrochemistry were performed, and we are going to continue these experiments. Thank you for your attention.